So these two functions, fixed update and first order intercept time. Fixed update is the main function here that actually does the controlling, and I'm using fixed update as opposed to just update. I could have used update, but I found that it's best practice to use fixed update when you have calculations that don't involve human input, but simply need to happen every set number of CPU cycles. This way, if you do have a number of different instances of the gun, for instance, running this calculation, they don't step on each other and interfere. Updates should be reserved for situations where at periodic intervals you've got player input that's going to control your calculation or actions. So all of this only happens if we've acquired an opponent, just to make sure that the opponent hasn't been destroyed or there was some error. Target position is now the position in world space of my opponent at this particular moment. So this is where it actually lives right now, where the jet has flown to at this moment. And the target velocity is its current velocity. Velocity is not a property of the transform, but of the rigid body that is associated with it, or has to be for something to be propelled, as our jet is. So we're going to use get component rigid body and then get the velocity property of that. And the direction, as I said before, is simply the vector or the line between this transform position, that is where the gun is, and where the target is. And so the easiest way to do that is to do target position in world space minus this transform. Since these are both vector 3's, this works out and gives you the nice line between them. Time now is this calculation where I'm going to call the function below, first order intercept time, and feed it in 3 parameters. Bullet velocity, which I've set above is 2,000 meters a second. The direction, which we've seen, is just the line of where the gun is pointing right now, or where it would be pointing if the target were stationary, and the target velocity. And then I let this calculation itself determine the time. Now, so what is time? Well, time calculates the time for the bullet to traverse to the estimated new target position based on the inputs, which are, again, how fast the bullet itself or the shell is firing, how fast it's moving. We know the current place in world space of the target in relation to the gun, and we know in what direction it's moving and how fast. So the time then is how long it takes for the bullet to get to this new estimated velocity. And all of this stuff is handled down here in this function. And I will say off the bat that the entirety of this code is something that I have borrowed after having searched for various versions of code that people have found useful to correct aiming for a moving target. This one seems to be the most useful. I think that it's a little bit overcoded for our needs. It handles some cases that I don't think we're going to encounter in our very simple example, but I felt it was best to just leave it alone, as there's math here that I don't completely understand myself. So I'm kind of treating this as a black box. I can explain conceptually what it's doing and also why it's called first order intercept time, because there's actually a bit of a calculus issue going on if we really wanted to try to estimate it, and apparently it's not possible to do full-on calculus in C#. So I made up this sad little diagram of what we're trying to achieve here. Here's our gun, a little simple thing colored red because it is the opponent. Here's our player jet in blue, represented as a cone. This is where it currently is in world space. So this is target position here. And then target velocity is what we know as of this moment right now is the jet is moving this way at a certain speed. All right. And here is the shell moving at its speed that the gun is deciding to fire right now. So the question is, where exactly does that gun aim? So what is it aiming at? Well, it's aiming at this. This is what we're trying to get at. It's the estimated position of the jet based on the current position, its direction and velocity, and the time it takes the shell to get to this new point. Because, of course, if you don't include that, then you're not going to be able to estimate where this is. However, if you think this through, it's a situation where the time variable is kind of part of both of these things. You would need it to be fixed. I mean, it's an independent variable, but we're pretending that it's fixed in one case or the other. And that's why this is called first order intercept time, because it's basically a first order calculation of what is really a sort of calculus problem, but it is one that kind of pretends that time is a fixed variable in one of these, or tries to split the difference between the two. We've seen in showing you that demo with how close the flak bursts are that it is close enough for our purposes. And so hopefully at least you'll understand what we're trying to do here. We've got certain inputs that we are sure of. We know where the jet is now. We know what direction it's going, how fast it's moving. We know how fast our gun can shoot its shells. And so based on this, we can come up with a rough estimate of where to aim and also what to set the proximity fuse to, so that ideally not only does the shell intersect where the target is going to be, but it also explodes at that point. Now, of course, as I've mentioned before, what this calculation cannot possibly take into account is that the jet may not simply continue flying in a straight line. It may move around, go in a totally different direction, and in fact that is exactly what planes have to do in order to avoid anti-aircraft fire of this kind. But we can only guess based on where it is at the current moment and the direction it's traveling and its speed and all of that. So that is what we're trying to do with first order intercept time. Once we have gotten this value for time, in other words, how long it'll take for the bullet to traverse from where the gun is shooting it to the estimated new target position, now we can say that, and this is where again you've got a kind of chicken and egg thing, because you're calculating the estimated target position based on the current position plus time times target velocity. So this is the velocity it's moving, we're assuming it's going in the same direction. And here is the time it takes for the bullet to get there. But of course, there was already kind of calculated based on those same inputs. So again, you see where we have a sort of chicken and egg thing that I believe could only be solved as fully as we could do it through calculus. But our approximation is working well enough to get those flak bursts pretty close. And just so that you know, before I added this in, and I was simply aiming the gun at where the jet currently is at the moment of firing, I found that what was constantly happening was the flak was missing my jet by a long way, and it was always exploding some distance behind where I was. So it was clear that the problem was that I just wasn't leading the jet at all. I was always trailing it, and the aim improved considerably once we put this in. So now we've calculated the new estimated target position, and now we can adjust the aim accordingly. So now the guns are always aimed slightly in front, and we'd be able to see that if we looked really closely at the jet, especially if it's moving kind of sideways in relation to where the gun is, you'd see that the gun is aimed slightly ahead of where the jet actually is, and that's because it thinks it's going to be further along. Then, in the case of the turret control, now that we know where the gun thinks that the jet is going to be in world space, we're only interested in the sort of horizontal component of that. So I'm going to take the y component of the vector, which is the up and down component, and I'm going to zero that out so that we are only interested in what would be essentially the reality if the jet were only like a car or tank or something traveling along horizontally on the plane and didn't have three-dimensional movement. And then we're going to use, for the rotation, a slurp. I could just do quaternion rotate, but slurp is a really useful function which does a smooth sort of traversal. As it says, it's a spherical interpolation between point A in world space and point B by a time t, which is clamped at 0 and 1, so it's got to be somewhere between 0 and 1. And here it's moving from the current rotation, where the gun is currently pointed, to where it would be looking based at the updated direction, which is the vector to the newly calculated estimated position. And I've set this down to 0.1, which is almost as, I mean, I could make it 0.001 or something, but 0.1 is pretty fast. If I am using this function for, let's say, a tank game and for the turret to traverse, realistically, turrets move much more slowly, and that's part of the challenge of playing that game, is you got to account for that. In the case of anti-aircraft guns that are having to do their best to shoot down a fast-moving jet, then you want them to be as agile as possible, so you can set this nice and low. And so this will now slurp. Now, if I had not set the y to 0, this would have had the effect of pointing the entire turret, not just horizontally, but vertically as well, directly at the target. But we don't want that. We want to handle the vertical part of it with the gun. So that takes care of turret control.